Okay, now let us consider the other case, which is that I know my location somehow. My robot, my agent does not have defected legs or something like that. It moves exactly the same. But my map, mind you, it's static, is not known. Except for the position where you are at, of course, will not be an obstacle. And let's say that you could, for the grid example, look into the neighbors. For the other cases, a generic case, of course, you could have one look ahead action, or maybe just apply the action to know the next little thing. So I say that my map is not known. So let's take another small example. And in this small example, of course, I am plotting the map, but believe me, the agent doesn't know it. You can see it because I am showing that to you, and my source, by the way, is known. So let's say this is what is my source, this is what is my goal, and my these are some obstacles around, and my agent cannot look at the goal, cannot look at the map. So that's only for your and my understanding. Now, can I still use the searches? So let's try to use the breadth first search first. Of course, I can first explore the source. I'm at the source, I know all its neighbors, one action look ahead. And let's continue with breadth first search. The second thing is around over here. So breadth first search, it'll go breadth by breadth. So from source, it'll go all nodes at the neighbors, which is 2, 3, and 4. Now there's a problem. So I cannot go and look at what are the neighbors explore to unless and until I go it. So the next thing that I need to expand is to over here, and therefore I'll have to physically travel. And mind you, this arrow is not inside my head. I don't know the map. In order to explore 2, the next step of breadth first search, I'll have to physically go to 2 and insert this thing into the fringe. Fair enough. I'm over here. Now to expand in 3, I'll have to physically go here and expand these 2 nodes, which is 6 and a 7. In order to expand 4, I mean, yes, I know it's a wall, it's useless, but the agent cannot see that it's a wall. It'll have to physically go over here and see that, okay, there's nothing to be done. It's a bit first search. A bit first search. Then I'll have to go all the way up to 5 to expand it. So this is a physical traversal that I will have to do in order to expand it. Then I get a 8, which is the only node, and add it to my frontier or my fringe. Now to expand 6, I physically have to travel over here to expand 6. So you see, what am I reducing? Every time I make a backtrack in the breadth first search sense, every time I say that, okay, let's expand this node, I physically need to travel to that node, which by the way is another search. And only when I travel to that particular node, I can say, okay, these are obstacles, these are not obstacles, these actions are feasible, these actions are not feasible, and these are possible. And I add it to my fringe. So it's a terrible search already. I need to travel too much. Even if towards the end I get optimal answer, How do I care? My robot has physically traveled an endless distance, which by the way keeps on increasing. The other way you can look at is I need my search online. The robot should keep moving so it doesn't sit and think. It acts instantaneously. And this breadth first search, it makes the robot travel so much in and around. And of course, the thing that I do is instead of BFS, I go DFS. Now my life is simple. Apply backtracking. 1, 2, 3, 4, 5, 6, 7, 8. Now there's a problem. I'm at a dead end. Now I'll have to, so I mean, my robot is of course physically moving. I did not show it. Now I need to backtrack. Now, luckily for this problem, I assumed that the actions are reversible. If U connects V also connects U. The edges are bidirectional. Otherwise, how to get from 8 to 7 while backtracking is a very big problem, and that may not be solvable. I may end up in a one way you can go, you cannot return back. If you cannot return back so many one ways, then there may not be even a path possible. So we assume that's why we use strongly connected component DFS in traffic and similarly in problems. There are no dead ends for sure. And because it's the first and only example, I say that the directions are bidirectional. So from 8, I go back to 7, then I explore that 9. Again, I'm trapped in a dead end. I come back, backtrack, 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 backtrack. And you go upon going like this, and you reach the goal. So remember that I have solved the problem. It's called as an online DFS, where the term online means number one, the decisions are being taken on the go. I'm not thinking by sitting at the source, which is my part. I'm acting every point of time. That's why the term online. The other is, of course, because of this, an added advantage is that I don't need to know the map and I can solve it without even knowing what the map is. We've again to mention solved it for a specific case where the actions were bi-directional. Remember, you will have to in the code use tricks to identify cycles. Now you've got a lot of memory. Memory was never the problem. So if you reach a cycle, you can just avoid going back into it. Again, you'll need a list of state action pairs which are tried, which are untried. So all those code modifications will of course be there. Now it might be inquisitive. Every time I tell you about something, I'm say that okay, this can be done, but you can use some heuristics to get it, make it optimal. This is how it's done, and usually it would be DFS. For different reason, we end up always saying that it's a DFS, but then I'd say that okay, you also have a heuristic function, so some heuristic is possible. Can I use that heuristic function? Yes. In DFS, how do you decide whether this comes first, this comes first, this comes first? DFS algorithm doesn't say that. It says decide whatever order you like. DFS never specifies the order. It never says first up, down, right, left. You can apply left, right, down, up. So at any state S, what I do is I select an action A which results in S dash such that S dash has the best heuristic value, and it's the same heuristic function that we studied in the A star algorithm. Heuristic function is available. All I say standing at S, the action that I applied is the one which minimizes my heuristic function of S dash, where S dash is equal to the action A applied to S. Simple enough. So this is the heuristic that I was always choosing for. And of course, that remember that if that state action pair is already selected, you don't select it again. Otherwise, you go in a cycle. So I'm only talking about ordering of actions inside the DFS loop. I'm not talking about going outside DFS and making a greedy action, in which case you might end up in cycle. So that's an obvious heuristic to take. Now, if you're taking this heuristic, all that you visualize is that your robot is going again and again and again. It's doing some exploration, and while exploring, it virtually comes to know about a good part of the map. And not only does it come to go about a good part of the map, it also eventually reaches the goal. And once it eventually reaches the goal, it stops, subjected to no dead ends, of course. Now, for the future runs, or for a robot may have to visit the same state multiple times, you could do one little trick as well. And that one little trick is, suppose there is a state S, one of these grids, and from this state, its neighbors are S1, S2, S3, S4. These are the only neighbors which are possible. And of course, there is a fictitious goal, and we say that everything is connected to the goal by what we call an estimate of heuristic function. Now, HS is of course the heuristic function for S. So this is assumed to be HS, the distance between node S to the goal. Can I improve it up? S, either the path will be S, S2G, or the path will be S, S1G, or the path will be S, S3G, or the path will be S, S4G. There is no other path possible. There is no other neighbor. And therefore, it's either one of the four paths. So the cost from S to goal will be the cost to go from S to S dash, where S dash is S1, S2, S3, S4, plus the heuristic value of S dash. And because there are multiple paths, I'll take the one which has a minimum cost. And that is a better heuristic value. Let's call it as the capital H. So I can, as I go along, actually improve the heuristic function. And guess what? Here, who said I need the old heuristic function? I can use the improved heuristic function. So, of course, there's a special case. This only happens if all edges are explored. If not, then use the bad one. Use the improved one if all of them are explored, otherwise use the bad one. So when you haven't seen anything, just use a bad one. So as you go along, you can actually improve the heuristic function, and this has a special term. This equation is called as learning the heuristic function, or improving the heuristic function with time, or improving the heuristic function as the robot operates. Why am I doing that? There's no harm. It's just a one-line equation. If you can improve something, just improve it. You're not making special actions to improve the heuristic function. So it's just one line. There's no memory problem. You can explicitly store the heuristic function for all states for this problem. It's not that I'm dealing with exponential memory for this specific problem. So if you can improve the heuristic function, make use of what you know, well and good. If you are really very inquisitive and eagle-eyed, as they say, you might be able to see that there is a kind of Dijkstra's which is happening with H. So if you explore these edges in an intelligent way, you actually get the distance function of the Dijkstra's. And if you explore all the SAS dash, you actually get the distance function of the Dijkstra's, and it fails to learn anymore because it has got the best heuristic function. So if your agent is anyways operating, you could let this thing run in the background for all the observations. So what did I change with DFS or online DFS? I first applied heuristic function, so I call it like a A-star-like algorithm. It is also real-time A-star, so just like online DFS, it's online A-star or real-time A-star, and it has a learning base because in the background, it's using this learning equation. So that's what I call as the LRTA star, where you make all the immediate motion, you make in all the motion of this part. So you reason, is this better? Is this better? And whichever has the best heuristic value, you choose this one. Maybe this was the best heuristic value you could have gotten straight. So you keep on reasoning which is the best heuristic value, which is the node with the best heuristic value, and keep on selecting that in the normal search framework of DFS. However, in the background, you also use this observation to learn the heuristic, and that's why we say it's derived from online DFS, the online A star or real-time A star, plus a learning in the background called as the learning real-time A star. And of course, with this, I conclude today. Thank you.